So as we were kind of alluding to in the beginning, when we were talking about inflammation, inflammation doesn't always work to solve the problem, right? And so acute inflammation is inflammation that's short-term, and usually the macrophages can clean up the damage by ingesting the dead cells and the debris, right? And we all go on our happy way. If acute fails, then you end up with sometimes what's referred to as chronic inflammation. And this is when the macrophages can actually form giant cells, and you can get granuloma formation. Does anybody know what disease typically goes into chronic inflammation and is pretty much diagnosed by granuloma formation in the lungs? Yep, tuberculosis. And that's what they're looking for when they're looking at chest x-rays. They're looking for these masses of white blood cells that form as they're trying to eliminate the pathogen, the bacteria, and they're not being successful. So the more and more of them are infiltrating into the area. So what is a giant cell? Well, what does it sound like? Yeah, macrophages that fuse together, so they become really big, right? They're giants. And the invaders, this is an important distinction. The invader's not destroyed, right? So this is a macrophage, say it's infected, and then another macrophage comes along, he's trying to help, he literally engulfs his friend. And he can't do it either. And then another one comes and another one comes, and they just keep engulfing each other, and they just get really huge. Granuloma, you've got these giant cells, but you also have what other cells that come into the area that distinguish it as a granuloma? Now you got T cell involvement. So you got macrophages, you got giant cells, and now T cells are coming on, and they're trying to help out because the macrophages aren't being successful. T cells are a type of lymphocyte, right? They're actually T lymphocytes, but a lot of times we just abbreviate it to T cells. So this is showing you two different types of granulomas that can form. This is a pretty good diagram I stole from the internet. So the top half is showing you a granuloma favoring bacterial cytal function, where there's the possibility that they might actually kill off this bacteria. So you'll notice that the bacteria are actually outside, a lot of them are outside of the cells, right? And you have necrotic macrophages, you've got apoptotic, oh my god, that word kills me, macrophages. You've got macrophage 1s, right? And they're classified in this state, like a macrophage 1 and 2, like a macrophage can go between these different states, right? This isn't two different type of macrophages. It's just how it's behaving at that particular time. And so you can see that they're talking about several different cytokines like IFN, what markers it's displaying on its surface, right? Helps to note what phase it's in, but this is a good phase for a macrophage. But you can see why it's a granuloma too, because you have the T cells, right? And these are Th1, so again a subset of T cells. You even have B2 cells. These are B cells, right? These would be ones that would maybe even produce antibodies that would help with this situation. You've got neutrophils coming in, and notice this neutrophil is eating up some of the bacteria. And maybe it'll help eliminate them. We're down here at the bottom, this granuloma environment, this architecture. They're containing the bacteria, but they're not eliminating it. So you've got these giant cells that are forming, right? And some of them are referred to become foam cells, and so they have a whole lot of lipids in them, like lysosomes are popping, but they're not doing anything, right? Again, they're not eliminating the invader. You've got mostly macrophages in the 2 state, infiltrating into the area. The B cells are regulatory B cells. And then also the T cells are regulatory T cells. So these are not actively involved in the situation and trying to solve the problem. They're just trying to keep it contained. So granulomas can go into different types of states, right? And this one favors the actual eradication of the bacteria. Where if you get a lot of giant cells and a lot of regulation happening and not a lot of destruction, notice again, 1 neutrophil, right? You're not going to really destroy the pathogen. This granuloma is just going to get bigger and bigger and bigger. And if this is the case of tuberculosis, Ashley, can you or one of you guys shut the door for me? Aubrey, thanks. Charlie's group is on break now. We need to coordinate our breaks. So if this is tuberculosis, which typically happens with tuberculosis, is that the granuloma it's going to be this progression. It's just going to get bigger and bigger and bigger. And you start running out of room in the lungs to be able to breathe, right? And that's why the common name for it, you would hear sometimes for tuberculosis, was consumption. You were consumed by it, right? There's a belief that Doc Holliday, right, died of tuberculosis, of consumption. Lots of famous people in the past. We have drug treatment for this, right? That's great. Except what else do we have? We have resistant strains of tuberculosis, right? We have extremely drug-resistant strains of tuberculosis. So how did this happen? Well, microbes always change, right? But we also haven't helped with this problem. And one of the problems with tuberculosis is because of these granuloma formations, it's really hard for the antibiotics to get to the bacteria. I mean, think about it. It's stuck inside the macrophage, right? So treatment, minimum treatment, is usually 6 months for tuberculosis. Can you imagine having to take several, not just one, several antibiotics for 6 months? Most people don't keep up with their treatment in relapse because they don't eliminate all the microbes. And then again, we're just putting that selective pressure on them, right? We're going to tend to push them towards being resistant if we keep throwing antibiotics at them and we don't kill them all in the process. So there's all kinds of, different governmentally sponsored programs where I think they basically follow the people around and take your medicine. Right? Because this is a serious problem. We also don't vaccinate against tuberculosis in the United States, do we? Very few people are vaccinated against tuberculosis. Some military personnel, for different reasons, have been vaccinated. Unfortunately, most people who work in prisons are vaccinated because the prison population, especially in Louisiana, has a lot of tuberculosis. Other types of jobs or things like that. Most foreigners that come from other countries have been vaccinated, right? They use the vaccine. Why don't we use it here? There's 2 reasons. Anyone know? One, it's not a very effective vaccine. It's actually a cousin that they vaccinate you with. It's not actually Mycobacteria tuberculosis. It's Mycobacteria bovis. So I think it's BVG is the abbreviation for the vaccine. Yeah, if we vaccinate you, we cannot do what test? The TB test. You will come out positive. Right? Because what that relies on is they put, again, BVG proteins in your skin. And if your immune system recognizes it, the white blood cells head to that area and you end up with a bump, and that's a positive result. Right? You get an induration, and that's because your immune system recognizes it. Well, it recognizes it because you've been vaccinated. right? But we use it as an early detection method for tuberculosis because you're not coughing up a lung until you're pretty seriously far along in this infection, right? So the only other way we would be able to check you is do a chest x-ray, right? We don't want to go around doing chest x-rays on everybody, right? So if they suspect, right, they're going to do the TB test. And we can quickly know in a matter of a couple of days, you know, if there's a potential that you have the infection. They're going to do further testing. But how many of you guys are going into the health field? Like almost all of you. So depending on what you end up doing and where you're doing it, you may have to have the TB test done maybe yearly or sometimes even every 6 months. So maybe 5, 6, 10 years down the line, right, you get a TB test done and it comes out positive. And you freak out. But do you have a reason to freak out? You might. Maybe you had a TB patient. Maybe you have a reason to be freaking out. Or it could be they've given you the TB test so many times and somebody screwed up maybe even one of the times and put it a little too deep or something like that. Or just, you know, we've injected it into you so many times that your immune system's like, hey, oh, I've seen that before. We essentially vaccinated you by giving you so many TB shots. That has happened to numerous people working in the health field, right? Then you get a little card, right? You never get another TB test done because it's going to come out positive. Instead, you then have to go for chest x-rays whenever the monitoring period or potential exposure has happened for you. So my ex-husband worked in a prison and was sent overseas by the military. He was vaccinated against tuberculosis twice. He goes to LSU. LSU gets a lot of foreign students. You have to go to health services. You have to have the TB test done. He says to the girl working at the desk, well, it's going to be positive. She freaks out. He's like, I just handed you 5 pages worth of vaccinations. It's on there twice. She's like, well, you have to have it done. It's like, okay, fine. A couple days later, he's like, honey, I don't understand. No reaction. I'm like, I don't know. I know it's a weak vaccine. I mean, but dude, you got it twice. I mean, you probably would end up with a positive TB. We're thinking about it. I'm like, it's a protein. Usually in like a saline solution. They usually have to shake the vial because, you know, the protein will settle out at the bottom if they're using a vial, which a lot of places do when they're doing high volumes. I'm like, did she shake the vial? He's like, I don't know. I'm like, I think she probably just gave you a saline shot because he didn't get a reaction. He's like, I'm good. I don't have to go for a chest x-ray. I'm happy. I'm like, dude, you need to go report that girl. One, she's freaking out. That's not good for an international student that comes in and is going to probably end up with a positive TB and she doesn't understand why that could happen. Well, he was vaccinated. So he was vaccinated twice. So there was a pretty high probability that he was going to end up with a positive TB, especially since the protein is from the same organism that they use for the TB test, the vaccine. So he should have came up positive, but I don't think she administered it correctly.
So other countries use the same vaccine also?
They use the vaccine, therefore we cannot use the TB test as early detection. Because if you've been vaccinated, you will probably get a positive TB test. And you will always get a positive TB test. Once your immune system recognizes it, pretty much always recognize it. You're always going to get a positive result. So you have to understand, you know, how this works and why that works and why we use it. So if we were to use the vaccine, we could never use the TB test again because everybody would come in positive. It'd be useless. That make sense? So, you know, it's I don't know. I don't know how I feel about it. But the other frightening thing is there's an alarming number of people in Louisiana that have tuberculosis. So, FYI. So is inflammation always awesome? Like the best thing that ever happens? No, granulomas could form, right? There's one bad thing right there. This is also like when the fire alarm goes off and the sprinkler system gets activated in a building. Yeah, the computer lab would be gone, right? Water, computers, last I checked, they don't mix, right? So, but we can't be selective with that, right? Sprinkler systems don't go, oh, computer lab, I'm just not going to turn on in this room. Not going to happen, right? Unless you set it up that way. So it's an all or nothing suppression system, right? A sprinkler system. So how is our inflammatory response similar to that? Right? Does it go in and go, check out? Like, oh no, she's okay. She's got the badge on. She's good. I'm going to skip that cell. No, remember what I say about those neutrophils? What do I call those guys sometimes? Suicide bombers. When they hit the building, that's it. The whole building goes, right? Including them, right? The bomber themselves. Okay. So our system is very similar to that, right? It's going to prevent the spread, right? But it itself can cause damage, right? So when the sprinkler system goes off, the fire is suppressed, right? It's not going to spread, hopefully, to the whole building, but it would damage a computer lab for sure. So same thing happens in our body. We'll prevent the spread sometimes, but there is a cost to that. We will destroy neighboring cells sometimes in that process. The good news is we're not unicellular organisms, right? We're multicellular. We could spare a few cells, right? It's all good. For the greater whole. Right, yes. It can get complicated, right? So enzymes, toxic compounds from our phagocytic cells are released and they can damage tissues, right? Normal, healthy cells that unfortunately were near the destruction zone. If it's limited, right, a cut on your finger, then damage is minimal, right? We can survive this, no big deal. Like I said, we could lose a few cells in that area and we can regenerate them, no problem. If it's a delicate system, right, like the membrane surrounding your brain, known as the meninges, or the spinal cord itself, right, this uncontrolled suicide bomber could end the whole system for us, right? So inflammation in those delicate areas, unfortunately, can cause more damage than help, and even loss of life. So does every time a cell in our body dies, do we have inflammatory response? All the white blood cells come running over to gobble them up? No. Right? Because if that was the case, you would be in a constant state of inflammation, right? Your cells are dying all the time, right? Red blood cells, 120 days, man, they're super long distance truckers. They're like, oh man, I'm done. That was the longest 120 days of my life. I'm done. Like, really done. So why would you not want to trigger inflammation every time a cell died? Yeah, you'd always be inflamed, right? So instead you're going to do apoptosis. This is programmed cell death. This does not trigger the inflammatory response. So our cells can die, right? And all the buddies don't come running over. But if our cell is damaged, right, from an invader or from, trauma, that's different. That is going to trigger. So priapatesis, we need to be able to recognize, okay, is that one just done, right? He's finished his super long 120 days, he's just done. Or are there the potential that something is going wrong here? So we have pattern recognition receptors, that are triggered when the bad guys are there. Right? We can recognize when this is not normal death for a cell. And in that case, we're going to trigger the inflammatory response. So how do we know? Right. Some alarm systems are pretty sophisticated, right? They know that it's not somebody who's supposed to be entering. Nowadays we got the video, right, monitoring. You can look up on the screen, you'd be like, no, that guy with the gun, don't want him in here, right? Your girlfriend, right? Your brother, your sister, right? You would probably let them in your house, right? You see on the camera, oh, okay, that's on chain, let her in. You know, guy with a gun, probably calling 911, right? So their system is pretty good like that, right? They have receptors. They're not using video cameras, right? They have receptors that can recognize general patterns of danger, right? Foreign substances. And therefore say, yes, inflammation is necessary. Call 911. Call in reinforcements. There's a problem. So when a cell dies, right, we have a way of knowing, okay, is this normal or is this, is something afoot? How should I respond? Or is there a response necessary? So remember, their world is molecular, right? So we're going to be talking about molecules. We're going to talk about receptors on cells. So the next is my favorite, with more favorite videos, which of course are on Canvas and YouTube, not Blackboard. These are shorter though. So the first one we're going to look at is the neutrophil chase.
Neutrophils are white blood cells that hunt and kill bacteria. In this spread, a neutrophil is seen in the midst of red blood cells. Staphylococcus aureus bacteria have been added. The small clump of bacteria release a chemoattractant that is sensed by the neutrophil. The neutrophil becomes polarized and starts chasing the bacteria. The bacteria, bounced around by thermal energy, move in a random path, seeming to avoid their predator. Eventually, the neutrophil catches up with the bacteria and engulfs them by phagocytosis.
Yeah, I know that everyone likes the sound effects. But that's pretty cool. He reminds me, the way he's moving, he reminds me of a protozoa, like a amoeba, right? Amoebas do the same thing, right? Phagocytosis. Oh, that's not the one we usually watch, but let's see. Nah, we'll do this one. That one, the sound effects were scaring me. So amoeba eats 2 paramecium. Oh, this one I gotta mute because he must have did it like on a projector in a classroom and you can hear all the kids talking. But look at that, isn't that cool? That's phagocytosis, baby. And then they're like, oh crap, we're trapped. Hurry up, try to get out. Oh god, it ain't happening. And then he's gonna release enzymes and they turn into mush. And he eats them. But that's what our white blood cells do all the time, right? They're engulfing and literally destroying what they engulfed by phagocytosis. So how do they know where to go? Oops, wrong one. I wanted this one. And I want for the video.
Neutrophils, taken from the blood of a graduate student, are mobile cells that will quickly migrate to sites of injury to help fight infection. They are attracted there by chemical signals that are released by other cells of the immune system or by invading microbes. In this experiment, tiny amounts of chemoattractant are released from a micropipette. When neutrophils sense these compounds, they polarize and move towards the source.
Looks like an amoeba, right? He's like, ooh, smells good over there.
When the source of the chemoattractant is moved, the neutrophil immediately sends out a new protrusion, and its cell body reorients towards the new location.
So, I mean, they literally follow orders, right? Wherever that chemical is, they're going right for it, right? And that particular cytokine, there's a whole group of cytokines just for chemotaxis, just for getting cells to go to that area, right? They can sense it and they just keep going towards it. And that's another one where that's faster than what they move, but they move pretty quick. But I mean, y'all, that was the first one. I mean, that's pretty simple, right? Just put some blood on a microscope slide and add some bacteria and watch what happens, right? And Staph aureus isn't motile, but remember, blood is liquid. So it was just being bounced around by thermal energy, by the normal collision of the water molecules with one another. It wasn't really running away from the neutrophil, but the neutrophil is going to chase him down no matter what, right? Because again, he can sense him. He's like, oh, yep, that's the bad guy, right? Those chemicals and stuff that bacteria naturally releases, the neutrophil has receptors on it, and it's going after him. He's not going to let him escape. Now, the details that you don't really see all that well in those are covered really well in the animation, because it happens pretty fast for the bacteria. But you could really see that kind of too with the amoeba, how it brings it around, right, and then engulfs it in that vesicle.
In phagocytosis, phagocytes are attracted to the area of invasion by chemical products of the microorganism, phospholipids released by injured mammalian cells, or by components of the complement system. The phagocyte moves into the area of invasion and then attaches to the microorganism. The attachment is mediated by a variety of surface receptors, including antibody, lipopolysaccharide, and complement receptors. For example, the C3b component of complement coats bacteria or other particles and then binds to C3b receptors on the phagocyte. This process of coating to enhance phagocytosis is called opsonization. The microorganism is then engulfed by the phagocyte into a vacuole known as a phagosome. Vesicles in the cytoplasm called lysosomes fuse with the phagosome, releasing digestive enzymes such as lysozyme and proteases into the phagosome. The structure resulting from this fusion is called a phagolysosome. Inside the phagolysosome, microorganisms are killed and digested. Finally, the digested contents of the phagolysosome are eliminated from the phagocyte by exocytosis.
So phagocytosis is taking it in and destroying it, right? And they were talking about, and remember I mentioned complement earlier? So this, where is it? I'm trying to get to the spot. There it is. So C3b is a complement protein that actually stuck to the surface of this bacteria. And that helped this phagocyte bind to it, right? Grab onto it. And so we have, those cells have receptors for things like lipopolysaccharide, which we know are gram. Who's got lipopolysaccharide in their outer membrane? Gram negative, right? So we have receptors for that we could, but that's a normal substance that's already on them. But also we produce antibodies, right, for specific pathogens. So if you already had an antibody, that antibody could bind, and then we have receptors on our phagocytic cells that would grab onto that. Any proteins that we produce, like complement protein C3b or antibodies that stick, that process of sticking to it and basically tagging it for destruction is what they called opsonization. And we're going to talk about that again later. But just, the more we talk about it, the more likely you're going to remember it. It's one of those terms that's kind of tough for students to kind of click to. But yeah, no matter what it is, somehow we've got to be able to literally grab onto the pathogen to be able to bring it in. So one of the things, right, is the complement system, another one of the proteins. All the proteins are labeled with C, which stands for complement. One of them is C5a, and as it says here, it's a chemoattractant. But there are other cytokines and stuff that can be released. But again, in order for the phagocytes to do their job, they've got to go to where the bad guys are, right? So they've got to know where to go. So the first is chemotaxis, chemical movement, right, in response to a chemical signal. Chemo referring to chemical, taxis, movement, right, like a taxi cab. That recognition and attachment can be helped by things like C3b or antibodies that can bind, and then we have receptors that will bind to it. Then the next step is going to be to engulf it, and the vesicle that it forms, that membrane encased compartment, for phagocytosis, this is referred to as a phagosome. And then, of course, when the lysosomes fuse, we just fuse the name, right? So now it becomes a Faygo Lysosome. Real creative there. But it dumps the digestive enzymes like Lysozyme, which remember, do you guys remember what Lysozyme does? Did I talk about Lysozyme? No, not yet. Not yet in this class. Cover it later in this class. It's an enzyme that digests peptidoglycan. So as you can imagine, very beneficial for antibacterial properties because it'll chew up the peptidoglycan made at their cell wall. But you know, other substances are released, right? And so hopefully we digest it and then we expel by exocytosis any debris. So chemotaxis, right? Chemical attractants. They could be phospholipids from injured cells, chemokines, or the specific complement protein C5a. We've got to get the cells to that area. And then we need to recognize and attach. So that's receptors. So there's lots of different receptors. Receptors that can bind mannose. Or we can indirectly bind biopsinins like C3b or antibodies. The next is we got to engulf it, right, and get it into that phagosome. And then that phagosome matures into the Faygo Lysosome when the lysosome fuses with it. The pH is going to be lowered. It actually becomes acidic, that environment. So destruction and digestion, more stuff might be brought on board in this process. Reactive oxygen, uric oxide, the pH, as I said, is lowered, it becomes acidic. Enzymes that will degrade molecules, proteins, lipids, mostly proteins. Defensins are molecules that can insert into the membranes. Lactoferrin is utilized to lock up the ferrin. Women produce lactoferrin in their milk. That's why it's called lacto, because you're lactating it. But again, the whole purpose is to bind to the iron and make it more stable in that solution. And then it said exocytosis to expel the yucky stuff. So our two main phagocytic cells that do this all the time, right, gobbling up the bad guys and digesting them and spitting out their parts, are your macrophages and your neutrophils. Remember, macrophages are called monocytes in our blood. But they're always in our tissues, right? They're all over our body. Where neutrophils are pretty much only in the tissue during inflammation, right? They're only going to be called there when they're needed. They don't hang out there all the time. So there's a distinction right there. Macrophages survive after phagocytosis, right? Macrophages, remember, big eaters. They do a lot of eating. And they don't just stop there. They're going to share that information with other components of the immune system. So it's important that after they eat it up, that they can stay alive and like tell their friends about it. Yeah, I just ate this really big salmonella. You know, you might want to get her number. Neutrophils, on the other hand, these guys, if they degranulate, if they release the contents of their granules outward, they die. So like when they go on their suicide bomber missions, yeah, they're dead. So why do we have these guys? Because, yeah, they're really good at killing. We're macrophages, right? They eat a lot, but they're not always all that great with killing. Sometimes they need their friends for help, like the T cell will help activate them to become more powerful killers. They're like, oh yeah, I recognize that bad guy. You know, you really need to soup up your attack here. You know, what you're throwing at it just ain't gonna cut it. Where neutrophils, right out the gate, man, those guys are serious. They're going to use everything they've got. They don't need any help. They're like, oh yeah, I got this. Mr. Macho, I'm going to take care of all these guys. Macrophages, as we've already seen with the granulomas, right, they can form giant cells, and then T cells start getting on scene. Right? And this is when, yeah, they're not cutting it, but they're like, oh, we're just going to wall him off. We're just going to keep him right here, right now. We're not going to let him escape. We're just going to keep piling up on him, right? Try and keep him in this area. Neutrophils, too, they're going to do the best they can to keep it where it is. Even if they can't handle it, right? If this is a super big bad guy, they will actually throw their DNA out of their cells, right? Because your DNA is huge, but it's compacted with proteins, with histones. They can release that and create like a spidey web, right? So they literally just shoot their DNA out of their cells, kill themselves, right? And become like a spidey net. So they're trying to, again, create a barrier, stop the microbes from getting out of that area. So next time, we're going to start going through the different white blood cells. And again, one of the main objectives is really to focus in on the functionality. So neutrophils are, as you see, really big phagocytizers. So are your monocytes, which is what your macrophages turn into in your tissues. And though dendritic cells, their first step is phagocytosis, they are always the ones that go the one step further, where they're going to share the information with the other cells. Macrophages can do this too, but dendritic cells are the main ones that are kind of your scouts. They'll actually even travel from the tissues back to areas where there's large concentrations of lymphocytes to activate your adaptive immune response, get things like antibodies produced, or cytotoxic T cells. With your lymphocytes, there are actually 3 different types, although they only show you 2 cells here. Under the microscope, the standard stain that we do to do a differential, and when you're counting, right, and keeping track of those major 5 that we look for in blood, the lymphocytes, you can't tell if you're looking at a B cell or a T cell, or a natural killer cell. You'd have to do a much more sophisticated stain to be able to tell the difference. Or now they use machines, of course. And sometimes you want to know, even within the major sets of cells, like T cells, you have 2 main types. And even within those types, you have subcategories. But we're going to stick to just the 2 main types. You have T helper cells and cytotoxic T cells. One of them has the CD4 marker on it, and one of them has the CD8. Anyone know what disease we're looking for a decrease in one of those populations? Because the virus targets them. So they're always saying, how's that person's T cell count? HIV. HIV attacks the helper T cells. It actually binds to the receptor on them known as the CD4 that they use to communicate with other cells in the immune system. the virus attaches to that and gains entry. Remember, I know I told you guys about the tribe in Africa. Everyone wished they were part of now, right? Because they're naturally resistant, because their CD4 is different enough that the virus can't attach. They're naturally genetically immune. Right? So again, you need that sophistication to be able to see, okay, well, they've got a drop in T cells. You know, is it an overall drop, both CD4 and CD8, or are the CD4s really getting annihilated by this virus, right? And so when that count drops below a particular threshold level, then that person goes from what's considered HIV to AIDS, which stands for Acquired Immunodeficiency Syndrome, because at one time they didn't know what caused it. And this is bad, right? You don't want someone to say, you know, you've progressed to the AIDS state, because now your immune system is deficient. You basically have to live like the bubble boy, right? Because your immune system is not going to save your ass, because it has been annihilated by the virus to the level that it's not functioning enough to help you. Does that make sense? So for lymphocytes, right, we talk about T cells, B cells, and natural killers. And then even within T cells, we talk about helper T cells and cytotoxic T cells, which are your CD4 and CD8. That's how we can distinguish them. But under the light microscope, the standard differential stain that we do, they're all just lymphocytes. And I'll give you guys some tips and tricks next time on identifying these under the microscope for AMP2, but you don't have to worry about it for in this class. But sometimes too, kind of knowing what they look like help you understand why they're named what they are and why they do what they do. So like neutrophils and eosinophils and basophils, notice all their names end in what? Fill. Because guess what they're all filled with? Granules. Hence why they're called granulocytes. What those are lysosomes, or, you know, different compartments within them that contain different substances. And because those substances are different, they stain differently when we stain them. So when we stain them, we use a combination of dyes. Eosin is one of the dyes. So guess what? Eosinophils, right? That's where they get their name. They get dyed by the stain eosin, which is a red dye. So their granules their granules are acidic, actually, I would think. Yeah, it doesn't matter. The important thing is they get stained by eosin. And that's why they got that name, eosinophils. So I always remember phils, right? They're all your granulocytes. They're all going to have this weird shaped nucleus, right? And they all have granules. Eosinophils, you can really see their granules, and they're going to be like a reddish-orange color because eosin is a red dye. Basophils are named after the fact that they stain basic with the basic dye that's in this mixture they use. And so they're going to be blue to purple in color. But guess what? The nucleus also gets stained purple. So a lot of times it's really hard to differentiate these from lymphocytes, especially if you're looking at them at oil immersion, because if you look at this big purple nucleus, it kind of looks granular. So you have to have a really discerning eye. But the easiest trick is, I always tell beginning students, if you see a big purple cell, look on the edge and see if you see a light blue thin cytoplasm. If you can, you're probably looking at a lymphocyte. And think about it. Never let their number 2. They're the most popular, right? These guys, basophils on the other hand, are at the bottom, right? They're extremely rare. Look at, in normal blood, 0 to 1%. And their close cousin, the mast cells, are what you would find in the tissues. They would stain the same. They have similar substances like histamine in them. Neutrophils, or polymorphonuclear cells, because again, the most predominant feature of them is their nucleus gets deformed. It's not that nice, perfect circle that we're used to seeing for our cells. It becomes multi-lobed and stretched out. Do you usually see their granules? No, but they have them. Sometimes, depending on how fresh the stain is or the slide is, you might see them. but they're almost the same color as the cytoplasm, like this orangey color, so that you don't usually see them. Again, hence why they're called neutrophils. They stain neutral. Like you don't see their granules, you don't usually see them. Macrophages are going to be your biggest cells under the microscope, right? In your blood, they're monocytes, and they're huge. Blue cytoplasm, big purple nucleus, and their nucleus sometimes will have a little indent in it, or even be kind of more stretched out and look like a horseshoe. Macrophages, remember, you're not going to see in your blood. They're going to be in your tissues. And same thing with dendritic cells for the most part. So mononuclear phagocytes, again, their nucleus pretty much stays intact, but they are phagocytic. They're going to engulf pathogens. Where these guys, eosinophils and basophils, kind of play off of each other based on their granules. Eosinophils, you're going to see them really go up with parasitic worm infections. So again, a doctor will sometimes order what's called a differential. And what they do, and of course a machine does this nowadays, unlike me when I worked in the lab, I literally did the blood smear, stained it, and sat with a little counter and counted the different types of white blood cells until I got to 100. And so that way I had a percentage, right, out of 100. So if I saw a whole bunch of eosinophils, then we knew we may be dealing with some type of parasitic worm infection, which was common in the armadillos. If we were seeing some neutrophils, we might be dealing with some secondary infection. If we saw a whole bunch of macrophages or monocytes in the blood, then we knew that we may be progressing along in the infection. If we had lymphocytes, a lot more lymphocytes, again, they're progressing much further along in the infection. Right? These come on later, where the numbers would increase later than early on. Where we were dealing with secondary infection, right? Because I purposely gave them leprosy, by the way, armadillos, to grow it. Because it won't grow in artificial culture, right? But, you know, sometimes they get secondary infection. We certainly didn't want that, right? We just wanted to grow Mycobacteria leprae. So if we saw a high number of neutrophils, that wasn't a good sign for us. That was an indicator. And the same thing is true for you, right, with disease, you know. And a lot of times when they do a standard blood panel, they order a differential, and it's going to give you the population of the 5 different groups of white blood cells that can be counted in the blood. And so looking at that, a doctor could kind of, you know, get an idea of what may be going on, right? And then they'll do a total count too, like a total white blood count, right? If that is low, that's not a good sign. If it's high, that's a pretty good indication that we're dealing with some type of infection, right? Because you shouldn't have more than normal, right? That says, right, we're responding to something. Well, then let's look at the populations. Do we have a lot of neutrophils? Well, we might be early on an infection, especially a bacterial infection. You're going to see a lot of neutrophils, right? As we progress further down, you might see more macrophages, then we'll see lymphocytes coming on, right? You'll see eosinophils if we're dealing with parasites, right? You'll see basophils and eosinophils increasing with allergic type reactions, right? Because they mirror each other with that. So there's a lot that can be said as these populations, you know, change in response to what's going on. And of course, it all relates back to what's their job, what's their function, what are they doing? Why are we seeing more of these guys? What's going on? Where are you at, potentially? But more sophisticated testing for HIV, right? Because we can't distinguish lymphocytes, never mind one T cell from another with a standard differential. That's a much more expensive test And again, they're only going to order that if, you know, they know you have HIV and they're monitoring. Does that make sense? You guys done? I'm done too. I can tell you're like, oh, shut up. No, just kidding.